do not share my screen. There we go. Okay, so today is going to be a review for test 5. It's mainly it's chapter 28, between section 6 to section 9. Okay. So first things, just to start with, that just like a reminder, the difference between parallel and series circuits. So if you have like two capacitors, like same resistance, if you put them in series, then you add them. You just strictly add them. But if they are in parallel, you don't really add them. Like you do add the inverse of them, then you take the inverse of that. For the current in a series, it's the same everywhere, but for a parallel, it gets divided. So like as you can see, there's a junction. As the current coming in, it splits to I1 and I2, then reconnects back to being I1. While in the series, it's just the same I everywhere. Meanwhile, the voltage is in the parallel is the same everywhere. So the voltage over here is the same as the voltage over R2. But in series, the voltage gets divided around each resistor. So with that in mind, we shall continue. So yeah, we start with parallel resistors. So in parallel resistors, as I just said, like if you have like any junction, so if you have any sort of junction, and this is what I mean by junction. And you have here a resistor, keep going, another resistor. This is R1, this is R2. So if this is I, we would have I1, and here we'll have I2. So the I is equal to I1 plus I2, while the potential difference on these 2 points, let's call it just delta V. This delta V is the same as this delta V2 as this delta V1. And this is what it's saying here. So potential difference around both of them is the same around each individual one of them. And if you want to find the total resistance, as I said, you will take the inverse of each resistor and add them all up, then take the inverse of that sum. So if you only have two resistors, then you will have the R total is equal to 1 over R1 plus 1 over R2. The inverse of that will equal to R2 plus R1. Okay, so what I did here, I just multiplied R2 here and there. So, and R1 over here and down there, giving me R2 plus R1 over R1 multiplied by R2. And the inverse of that will just equal to R1, R2, and this, then there's sum. Okay, but just keep in mind, this is only for two resistors. If there are three resistors, it's going to be more complicated than that. Just wouldn't be as straightforward. Okay, so any questions so far? I'll take that as a no. Okay. Oh, well, that sucks. Okay. Okay, so we have those four resistors, and we want to find what is, we want to just put as one resistor. What to do? Let's call this like R1. This is VR2. Let's call it R1, R2. Let's call this R3. And this is R4. So how can we find the total resistance? By combining all those four resistors. Okay, it seems someone trying to reach. Just 1 second. So then someone's trying to join in, but they can't. Or maybe they just did. Okay. We'll just shall continue. Okay, so as I was saying, for those four resistors, how can we find what would be the total resistance? We can first start with R1 and R2. So since R1 and R2 in parallel, we will need to find how to find their total resistance. Let's call it R1 and 2. Just simply use the one we found here. So R1, R2 will equal to R1, R2 over R1 plus R2. And that will equal to, this is 90 multiplied by 45 over 90 plus 45. That will equal to, that will equal to 30 ohm. So now, what we have the following. We have here a resistor with 10, then another resistor with 30, okay, so this will be 25, this will be 10, and these two combined give us 30, so this will be 30 ohms. Wait, so the one on D12 is not right? Okay, well, let me change that really quick if people are trying to join. Oh, the one on PAL is not the right one. Okay, well, I can't really do anything about the one in the PAL D12, but yeah, so sorry for everyone who can't join there. I can't really do anything about that. Anyway, let's keep going. Is PAL today? Yes. Okay, well that now makes sense why people can't really join. Okay. Well, then just wait a couple of minutes, then everyone else joins. Or maybe, oh no, it seems that whoever in that meeting, they're already here. So we are fine. So far, I think. We'll see. Anyway, okay, so now we have, this is, oh, this is ohms. Looks a bit weird, but this is ohms. Okay, so now we have 30 and 10 and 25. So what is the total of that? Since all of them in series, you can just add all of them. So that would be 10 plus 30 plus 25. This is equal to 40, so it's 65 ohms. Okay, any questions about anything I did? Take that as a no. Okay, then we move on voltmeters. What is a voltmeter? And that's a question for you. I can give you hints. You can see it from the name. So if you just split it into two parts, volt and meter. Yes, yes indeed, measure volts. So okay, so yeah, voltmeter measures volts. Voltage. Yes indeed. Okay, well then how to use a voltmeter? Does anyone know? Okay, so one of the main things for voltmeters are that you can take them, that the resistance inside of them, so they are of a voltmeter, is equal to infinity. You can say that. And that is important. So that means there's no current passing in the circuit, so it blocks all of it. So then at each end, the potential difference around the voltmeter would be the same as the battery, or as around whatever it's measuring. So if you took a voltmeter and put it in series, so this is V, since it has a resistance of infinity, it's going to block the whole circuit. So you don't put it in a series. When you want to put it, you just put it in parallel to whatever you want to measure. So let's say you want to measure what's the voltage around this resistor. You put it in parallel to it. So this will be V. And we can just remove the other one. Okay. So let's say that this voltmeter is measuring 8.5 volts. With that, how can you find the resistance inside the battery? So this is a battery, as you can see, and as any battery does have an internal resistance, and the internal resistance is this small r. So for a perfect battery, if you just have like the 9 volts in here, this is being the 9V, and just your 17, you can easily find the voltage around it by using the number equations that you have. First thing you need to find what is the current. So you need to find what is I, and I is equal to V over R. So that'll be 9 over 17. But then if I want to find what's the voltage around this resistor, so then you just put it back. Delta V is equal to IR, which is equal to the 9 over 17 multiplied by the 17 of the resistor itself, to just give you 9. So if this is the only resistor you have in the circuit, you will find it to have the same voltage as the battery, being the 9 volts. But if you measure it and you find it's less than the total voltage of the battery, that means that the voltage is being distributed somewhere else. And that will go in this small r, which is the internal resistance of the battery. So if you want to find what is the internal resistance of the battery with this information that we have. Okay, hello, hey Angela. I think most people figured out, and most of them are here right now. But I don't know what can I do about the changed link. Anyway, moving on. So if you want to find this small r, how can we find it? Well, you can simply use, you know, that the delta potential difference of a loop is equal to the potential difference around each component you have. So you would have the potential difference of the battery, this is being the battery, plus the potential difference of the small r plus potential difference of the big R, and all of these should equal to 0. So if you know this is 9 volts plus something, we don't know what is it, and this is 8.5, but always the resistor has a negative voltage compared to the battery, so we'll just have it as minus 8.5 should equal to 0. So you know that this is equal to negative half a volt. So then you can easily find what's the resistance as following. You do have the 9 volts should equal to an I plus small r plus big R. That's equal to small r is equal to, oops, is equal to negative half. I over big R is also equal to negative 8.5. That means that your I is equal to 8.5 over 17. Should we believe it's equal to half? Yes, it is. It's equal to negative half. So that means your R is equal to 0.5 over 0.5, which is equal to 1 ohm. So this is 1 ohm. Does anyone have any questions about that? Okay, so moving on. We then go to getting grounded and know what's the grounded part in any circuit. So if you first thing, usually in the beginning, it's not really clear why do we need grounding. So grounding is simply just having a small wire and you connect it to the earth. So which connected to the ground. That's why it's called grounding. And it really helps that if you have a lot of components, like if you have a circuit and has a lot of components in it, charge can easily accumulate on them. So you need some sort of release to those charges. And that's where the grounding comes. So it's really important that in anything you use that uses electricity that has grounding in it, because like inside of your computer or phone, there's a lot of resistors and capacitors, and they can easily accumulate charge in them, and that might hurt the machine itself. So that's why they need grounding to get a release of that excess charge. But just keep in mind that when you have like this component in your circuit, it does not change anything in the circuit. It doesn't affect it by any means. It just in a way give you a reference point. So let's say you do have a battery and you do have a resistor. And they are grounded. Say like this is 10 volts, this is 5R. It's going to be everything as normal. If you want to find what is the current, if you want to find what is I equal to, I will just equal to the 10 over the 5 equal 2 amperes. Same thing, nothing changes. The only thing is what happens that at this point, you do know that the voltage is 0. So if the voltage here is 0, you can then compare, you can find like the voltage and any other point and just know what's the value. So then you don't need to keep using the delta change in V, because the delta change in V is equal to the final minus the initial. And if you just put the initial as 0, then you know you just need to know what is this. You don't really need to know what is the initial. So we just put this as 0, and that would help you to find the potential at any point. So for example, since we know at this point it's 0 volts and the potential difference around the battery is 10 volts. So if you want to look at this point, this also has to be 10 volts compared to the ground. Because, from here to here, it's 10 volts difference. So if here at the ground is 0 volts, that means at this point it has to be 10 volts. The same thing, if you just moved it to here, this also has to be 10 volts. Because it's still just around the battery. There's no resistance in between to change it. And that will be more clear once we do exercise 30. So let us do that first. Okay. So yeah, let's solve this one. Okay, so yeah, this is 9 volts, this is plus, this is minus. We have resistance here being 2 ohms, and we do have another battery here. This is plus, this is 6 volts, and this is minus. This is 1 ohm. Okay, so it asks us, we need to find what is the potential at points A and B. This is being B, this is being A. Okay, so again, let's just see. Since this being the ground, you just simply say, you do know that at this point, the the potential will just be 0 because it's just right at the ground. And since you're around a battery and you know that the potential difference around the battery is 9 volts, this is 0, that means that here it has to be 9 volts. Okay. Okay. To keep going in this, we first need to know what is the current running in the in the circuit. So you do have 2 batteries, and as you can see, they're opposing each other. So one of them would have current going this way, and the other would have current going this way. So in a way, you can just simplify it and make it like take the difference between the 2 batteries and just make it 3 volts. So this will be 9 volts minus 6 volts, which is equal to 3 volts battery. And you can still have our 2 ohms. And here's our 1 ohm. And here is the ground. This is 1 ohm. This is 2 ohm. So it gets quite simple now. If you just want to find what is the current going through here, what is I will equal to the overall potential, which is 3V over the sum of the resistors, which is R1 plus R2 to 3V, 2 ohms plus 1. So just going to be 1 ampere. Okay, so if this, the current is 1 ampere, then you can easily find what is the potential difference around this resistor. So if you want to find what is the potential difference, it's delta V. It's equal to the 1 ampere multiplied by the 2 resistance, so be 2 volts. So then we know here at this point there's a delta change in 2 volts. If we have this 9, and since the resistance opposes the battery, so it'll just decrease by 2. So if here is 9, then we have at this point it will be 7 volts. Is that okay? Okay, well, if that's okay. So, okay, so now we know that the potential difference around this battery is 6. What would be the potential at B then? Okay, does anyone know? Just uh, throw a guess. If you know that the potential difference of the battery is 6V, yes, yes indeed, they're gonna be 1 volt. And you can check that again. If you looked over here, the change of this one is the 1 ampere multiplied by the 1 resistance equal to 1 volt. And it is indeed 1 volt. So here's 0 and here's 1. So that would be 1 volt. And there you go. You can find, so then you know what is the potential at points A and point B with the reference to the ground. So B will be 1 volt and A will be 9 volts. Okay, any questions about this? Okay, now we get to the big boys, the RC circuits. So the RC is just basically the R means just resistor and capacitor circuits. And what happens is if you get a capacitor with filled with charge in it, so you do have positive charge on one side and negative charges on the other side. And they want to get to each other, but they can't because you have here the circuit is open. So once this is closed, but what happened is then the positive charges or the negative either would have a way to get to the other side. So the positive would then just start running around, passes by the voltage, passes by the resistor, going all the way to the negative. But we do know that for a capacitor having a charge in it, it contains voltage, has a voltage around it. So what is the voltage inside a capacitor? Does anyone know? Or what is the equation? Okay, so the voltage of a capacitor is the total charge in it divided by the capacitance of the capacitor. But for a capacitor, it has only a specific amount of charge. Let's just call it Q naught, or as it says here. And oh, there you go. The voltage of the capacitor is Q over C. So as the positive charges go all the way around to the negative, the time, like the quantity of the charges will decrease over time. So the voltage itself is not going to be constant. Like this voltage, it's just at the first instance. Once you close the circuit and you have like a free flow, then that would be the voltage at this instant. With the initial voltage would be, you can find it using the initial number of the initial charge on the capacitor, because the capacitance that doesn't change. That's just a property of the capacitor. But as time passes, less and less charges would be accumulated on one side compared to the other. So also the voltage would decrease. So over time, over T, the Q decreases because just the number of charges keep traveling all the way around. As this decreases, also the voltage decreases. So you can just put the voltage equal to the charge over the capacitance. It's going to be a little bit more complicated than that. So yeah, so as I said, like once you close the switch, going to be less charges in one side, as they have now a way to go to the other side. So the charges decreases over time. So just if you just looked at the potential of the capacitor, it just in general is at any moment of time, the voltage is the number of charges at that time divided by the capacitance. And using Kirchhoff's law, we have delta V loop is equal to 0. So it's equal to the delta voltage of the capacitor plus the voltage around the resistor. All that should equal to 0. Just put everything in, the voltage of the capacitor is Q over C, as from here. And over resistor, just IR. All that equal to 0. So if you divide by R, just now have Q over RC minus I equals 0. And since, this I represents the current going in the circuit, or the currents in the resistor, because the capacitor doesn't have any current in it. Like this is just empty. This is whole, there's nothing goes through that. When we say the current, it's just the current in the circuit. Okay, and here what I just said, that since over time the voltage decreases, the current decreases, so, and since current is equal to the change of charges over time, and it's decreasing, so it's negative, I put that in here. So negative will be positive, equal to 0. That's not really important. What's more important is this. So like if you just played with this equation more or less with some integration, and I know most of you are not really interested in that, you can reach this conclusion. So if you want to find what is the amount of charge in the capacitor at any moment of time, all of what you need is the initial amount of charge in the beginning, then some factor, and that factor is being e to the power of something. So it's e to the power of some sort of time. And what it means is, if we have a graph here, this is being time, this is being q. This is q naught. So we know that over time, the charge will just keep decreasing. And that decrease is not linear, because that just makes things too simple in physics. And for so many reasons, that's not the case. It's gonna look more like this. And this is called exponential decay. And that represents by this factor, e to the power of negative something. And it's negative because it keeps decreasing over time. Like the more time passes, the smaller this number is, so the smaller q is. And we find that it's negative t over rc. And luckily enough, rc is some units of time. And we call it the time constant. So depending on the combination of the resistor and the capacitor and the capacitance, it'll give us this time constant tau. And this time constant is important as why? Because like let's say that RC gave you, I don't know, like 3 seconds. Let's say. So those 3 seconds mean after the first 3 seconds passes, you know that this Q is 0.6 of the initial Q. And after another 3 seconds, it will be like, I'm sorry, this should be 3, this should not be 6. And after another 3 seconds is going to be even less than that. It's going to be like 0.1 something. So in a way, it gives us like a step function. Like, after each individual amount of time, you know how much the Q will be. So you don't really care about what's in between. You can always find it. But in a way, it gives us some sort of reference. Yeah, after 3 seconds, definitely you only have 0.3 of the initial charge and so on. And that number is constant because it only depends on the resistance in the circuits and the capacitor. So it only depends on this R, and this R doesn't change, and this C does not change. That's why it's a constant. But using that just allows us to find what is the potential difference around the capacitor. So for the capacitor, with this resistor, that allows us to know how delta V change over time and what is the current, how the current changes over time. It's simply the same thing, just add this factor of negative e to the power of negative t over the time constant. Just the same thing, it's just this factor that one matters. Multiply by the initial. So any questions about that? Okay, your voice. Do you have a question? Okay, because this part is really important. Because like it can give you a lot of different things tomorrow in the test. So you need to ask questions, anything that you feel like, yeah, I don't really get that. It's really important to say now. Okay. So let's just first do exercises 33 and 34. Keep going. That hopefully will give you a bit more sense what is going on here. Okay, so 33. What is the time constant for the discharge of the capacitor? Okay, so let's just draw this first. Oh, there's two resistors. Oops. So it's asking what is the time constant equal to. So just using the equation, we simply know that the time constant is equal to RC. But if you want to know what's the time constant for the whole circuit, that means that you need the total resistance and the total capacitance of the capacitors. So we can simply find what is the total resistance. What is the total resistance equal to? Okay, does the capacitor have any resistance? Okay, I'm also, yeah. Yeah, does the capacitor have any resistance? Okay, there's no battery in this circuit. So you can safely assume that the capacitor itself would be the battery in some sense. It would be the thing that gives you the voltage. So the source cannot be the resistance itself. So the only resistance we would have is just two of those resistors. So just going to equal to 2K ohm. And for the capacitor, it's similar to as if it's a battery. It's not the same, but if they are in parallel, you can just say that they would share the same, they would have the same capacitance. Okay, if those two numbers were different, those are different. That's a total different story. And it's not like you're not up to that level to know how to solve that. So just for now, if it gave you the same two, the two being the same, you can just take one of them. Because as if it's a battery and the battery in parallel is just the same. Okay, so that means our time constant is just going to equal to 2K ohms multiplied by 2 microfarad, and that will equal to 4 milliseconds. So the time constant of this circuit would be 4 milliseconds. If you only had one resistor, this is going to be 1, and it's going to be 2 milliseconds. So it's going to decrease. So let's try the big F. If our total is equal to 1 kilo ohms, this is equal to F, then tau is equal to 1 kilo ohms to 2. And that's what you would expect, that when the resistance decreases, also the time decreases. Because look at here, if R decreases, T will decrease. Same thing. Okay, any questions about that? I'm muted. Okay, now. Okay, you gotta say something. Makes sense. We're here. Okay, we'll see. Moving on to 34. So it's just the same thing. Now you do have your resistors in parallel and your capacitors in series. So just doing that really quick. Okay, this is 1 kilo, 1 kilo, 2 micro, 2 micro. Okay, so it's just the same thing as a battery. If you have a batteries next to each other, just add them up. So I can just simply, so then the C total would just equal to 2 micro F plus 2 micro F equal to 4 micro F. Okay, so what about the total resistance? As anyone know? Any questions about what I just did? Okay. Okay, so now just recharging an empty capacitor. So if you put an empty capacitor in a circuit with a battery in it, it will start filling up. So if you do have a battery, you always need a resistor. And here is, and why you always need a resistor? Because, okay, because if you remember that your tau is equal to RC, so if the resistance is 0, if this is 0, that's just all that will equal to 0. So if this is 0, this will blow up. So if this will blow up, that would just be 0. That means, like if you have e to the power of an infinity, that just equals 0. And if that means that just the charge is going to be as it is, it's not going to decrease or increase or anything. So as if you don't even have a capacitor. Have a capacitor. That's why I always need a resistor. Yeah. So anyway, like if this is empty, so that's the positive charge like on the battery would just be moving normally as if there's nothing. Then it will be stopped by this layer. So have a positive charge accumulated over here. And this positive charge will attract negative charge on the other side. But over time, the capacitor has only like can take so much. So over time, just this will be charges be accumulated over here until it carries as much as it can. And after that happens, just it's gonna stop taking any more charges. So the current will stop. So the same thing we're seeing here. So yeah, if the initial charge that the capacitor would have, or the maximum, I'm sorry, this will be the maximum charge that the capacitor would have, is the capacitance multiplied by the potential in the battery. Because if you just see it, just the same thing, we just rearranged it. We said before that it's Q over C, so that means just change it, Q will equal to delta VC, which is the same thing here. But if you want to see how the charge will in the capacitor itself will be, it will start decreasing over time. So it looks something like this. This being Q naught. In the beginning, it has this is time. This is Q. So in the beginning, it doesn't have any charge. So it wants a lot of charge as much as it can. So you see, it increases really fast in the beginning. Then over time, it just has enough charge in it that it can't take any more. So it slowly taking charge and just reaches something called an asymptote. So it would only reach this Q naught over at time equal infinity. So yeah, and that's what we showed here. As time goes to infinity, as this goes to infinity, because e to the power of negative infinity, which is 0, so just 1 minus 0, so then finally the Q will equal to Q naught. The same thing will be for currents. Currents, it just will be in the beginning really fast, but then over time, it's just going to decrease with this same factor. And last thing would be this stuff to think, try to solve. So we want to find the time constant for this charge of this capacitor. How to find that? I think we already did something similar and even harder. What would be the time constant equal to? Oops. So it would take 4 seconds to discharge, to fully discharge. No, what is the time constant? Yeah, so the time constant is equal 4 seconds. So yeah, after 4 seconds, yeah, so then will be the answer. So yeah, after 4 seconds, there only remain 0.3, I believe, from the initial charge. After another 4.4 seconds would be 0.1. And after, so this is 4 seconds, this is 8 seconds. If we kept doing this, like after 20 seconds, we would have 0.001 charge left, which is basically 0. Okay, so yeah, this is the last slide I have. Does anyone have any questions? Let's just stop recording.